Right, this recording is to help you with lesson 3.05, exponential and logarithmic models. Alright, the first part is pretty simple as long as you have your calculator. You just need to match the equation with the correct graph. So let's make sure that we're just typing this into our graphing calculator properly. All right, and we want to type in y equals 2 times e, the x divided by 4. And when I graph that, I get that model, or that equation there, that line, which is, I believe, matches up with graph B. Alright, number 11, we have to find the missing information there. So we are given the model A equals 500e to the RT. Well, if A is 1,292.85 and T is 10 years, because we have T equaling 10, let's solve for R. So we'd have to divide each side by 500 first, and if we want to do it this way, we can. I'll do it on my calculator. 1292.85 divided by 500. You get 2.5857. We have to take the natural log of both sides to get rid of the e. I'm just going to estimate there around. And then divide by 10. So when you divide by 10, you get about 0.095, which is your 9.5%. Notice that you are going to be using the 0.095 when you plug it back into your equation, not the 9.5%. Your percentages need to be written as decimals. All right, now to find the time it doubles, if you're starting with 500, double that as 1,000. Right? And plugging everything we know back in, we now know that R is 0.095. So let's start by dividing each side by 500 to get 2 equals e to the 0.095t. Take natural log of both sides and divide by 0.095. So t is approximately 7.3 years. For the next one, we are going to graph it on our calculator and see which one grows at a faster rate. All right, if you see something in double brackets here, that refers to the greatest integer function. And you can graph the greatest integer function on your calculator. So let me show you how to do this. All right, if we need to graph the greatest integer function, well, let me just type the rest of this in, 1 plus 0.075. And then they have the greatest integer function. That is math. Go to number, and it's int with the parentheses, so number 5. That means your greatest integer. Let's see, I want to come back here and make this a point. And then we have x in there. All right, the second one was 2, or e, the 0.07x. So if I graph those, we're going to have to change our viewing window. Let's change this to 0 to 60 maybe. Oh, we don't even need it that high. So this is just really playing around with your window to see what's the best representation there. It's a little bit better. And there you can see the second one is growing a little bit faster rate. It is on top of that first line. And that would be your e to the 0.07x looks like it's growing a little bit faster. All right, for the next one, the population P of a city is given by the equation there. T is 0, which represents the year 1990. According to the model, when will the population reach 150,000? So we're going to replace P with the 150,000 and work backwards to solve for T. So let's start by dividing each side by 105,300. That would give us 1,500 divided by 1,053 e to the 0.015. Take natural log of both sides. And then divide by 0.015. And you should get T is approximately 23.59. Well, what year will that be? You have to add that onto your starting year of 1990. So 23.5 years will be in the year 2013. For the next one, we have the model n equals 100 e to the kt, where t is the time in hours. If n is 300 and t is 5, estimate the time required for the population to double in size. So the first thing we need to do is we have to solve for k. Before we can find out how long it takes to double, we have to know what k is. So we plug 300 in for n and 5 in for t. And we work backwards to solve for k. So divide each side by 100. Take the natural log to get rid of e. And then divide by 5. So natural log of 3 divided by 5 is 0.2197. Okay, we're going to rewrite our equation now with the 0.2197 plugged in for k. And now we're going to look to see how long it doubles. So if we're starting with 100, double that is 200. So divide each side by 100 to get 2 equals e to the 0.2197t. Take the natural log of both sides. And divide by 0.2197. So on your calculator, that's approximately 3.15 hours. The last one, we need to complete the model by solving for k first. So let's plug in what we know. They're going to let x equal 5 in hundreds and 2.5 in thousands when we solve for k here. So they're going to start by dividing each side by 10 to get 0.25 equals 1 minus e to the 5k. It looks like they would subtract 1 from both sides to get negative 0.75 equals negative e to the 5k. Multiply both sides by negative so they turn into positive. Take the natural log of both sides. We're now down to here. Divide each side by 5, and you get k is approximately negative 0.0575. So we're going to rewrite the model with our value for k now plugged in there. All right, part B, estimate the number of units that will be sold if advertising expenditures are raised to 700. So this time when x equals 7, let's see what we get. So we plug 7 in for x, and we can use our calculator, and you should get 3.314. And remember that is in thousands, so that's 3,314. Now, you don't have to change these to decimals. You can leave them all as the 500 and 2,500, and you should get the same answer in the end. So if you don't want to change them to 5 and 2.5, you don't have to.